Usually the first thing I like to do is talk about the relationship between voltage and current and a conductor. And the easiest way that I have been able to find that kind of puts it into a physical sense is to liken it to like a plumbing system. So if you think of the pressure behind in a plumbing system as the voltage, because voltage doesn't flow through a conductor, voltage is just the pressure behind it. The water that would flow through a pipe is actually the current flow, and then the pipe itself would be the conductor. So in that same relationship, the higher the voltage with the same size conductor, you're going to have more current flow, right? You want to get more volume or less friction in the pipe, you make the pipe larger. So friction makes heat in conductors, and the more current you got flowing, the more friction you got, the larger the conductor you need to keep it all within a reasonable temperature. Conductors are insulated generally. Like this is a coil of wire that we call this magnet wire. And what it is copper wire, but it's got an enamel coating on it. And it's the wire we use to wind motors with. If you look at this over here, so that each individual turn is insulated from the one that's adjacent to it. So if you get a break in the wire or a scratch in the enamel or you overheat the conductors, then you get a short in the winding and eventually a breakdown. So I just need to make sure everybody understands that before I move on, because it's a critical part of motor theory, as is electromagnetic induction, which is the concept of passing a field or a fixed field through a multitude or a single conductor to create voltage induced into it without contact. I've got a little demonstration, and we can even kind of probably gather up around it. So in order to get electromagnetic induction, you need a magnetic field, a conductor, and motion. A conductor is a material with free electrons, so a good example of that is copper, aluminum. Essentially what the voltage is doing, or the pressure, is it just kind of starts a chain reaction of those free electrons to move. And the reason, like, you can turn your light switch on, and unlike maybe in your plumbing, you got to wait on the water to get to the other end of the pipe. All the pressure is doing when you apply the voltage, you turn on a light switch, the light comes on immediately, is it's taking one here and it's bumping it into the one next to it. It's knocking another one off the end to do the work. And then it just continues that chain reaction. So that's why when you turn a switch on, it doesn't have to wait for the current to flow all the way to the light. There's one already sitting there waiting inside of the conductor to jump right in there and start doing the work. We've got a thing set up over here. We use this. You guys can kind of come around here if you want. Check this out. We use this thing to check what we call magnetic neutral on DC motors, and I'll kind of get into that a little bit later. But right now, the only reason I brought this over here is to use this little microamp meter that's on the front. And what I want to illustrate here is that I've got right here a 100 turn coil and a magnet. This is just a permanent magnet. And if I pass this magnet into this coil of wire, you can see how I'm inducing first one way and then the other way. That's essentially AC current. I'm making AC current just by virtue of passing this through this loop of wire. Now if I take and I attach it to my 200 turn coil, what do you suppose will happen?
Twice as much, huh?
Exactly. So essentially I'm just making AC current right there, just like that. And that's how a transformer works, because in a transformer you've got a building and collapsing field because it's AC. There's no maybe electrical connection between the primary and secondary, but it's actually just inducing a voltage or a current into, you know, a secondary winding. Same thing in DC motors, same thing in AC motors. This is essentially the basic concept of much of motor theory. We either got a permanent magnet or we will pass current through a coil and we'll make current. Unless you got two in parallel there now.
So that cancels them out?
Well, you can, it will a little bit, but if you hook them in series and put them together, you'll have more probably. Here, just do this. Yeah, you gotta take one of those. Open circuit. Yeah, I just stripped off enough there to get that on there. So in that light, what like say an AC generator, whether it's at the power plant or whether it's in your plant or whatever, what it does is it's got 3 phases in it, and each phase is 90 degrees electrically out of phase with one another. So as A phase rises and at its peak, B phase is beginning, and when B phase is at its peak, C phase is beginning, and so you always have a potential field moving in AC 3-phase. Single phase is just one of these, while 3-phase you have all 3 phases working together at the same time. One of the reasons you can't have larger single-phase motors is because they can't pull that off with just an alternating field. We won't get into a lot of single-phase stuff today, but I did want to express the difference between that and DC. DC is just a solid potential. Now, this is theoretical DC. If you put a scope on the output of a DC drive, there's going to be all kinds of chop in it, but the relative potential stays the same. It does not cross back over to zero. It never goes negative. It's always in a positive way. The only time you'll see that kind of DC is off like maybe an old MG set or something like that. But it's never crossing zero. Like, if you see, this is crossing zero and going negative with every half cycle. Power's distributed in the United States of America at 60 cycles per second, so this happens 60 times every second in the United States. And then, as opposed to DC, which is always in a positive potential. Now, I like to start with DC. DC may seem a little more complicated. In theory it is, but it helps segue into AC theory much better if we get a concept of how a DC motor works. These are the main components. As you've got shunt fields, and in this particular one, that's a picture of a 4-pole field frame. And then these are interpoles here, and we'll talk about the function of those. A lot of the more modern motors don't have series fields or stabilized shunt capacity. There's reasons for that. Most of it has to do with the more advanced drive technology than it does anything else. But the function of a series field in a DC motor is to boost the torque when you have a heavy load to start, particularly at low RPMs. So you need some extra boost, some extra torque to start, say, a difficult load, like maybe a mixer or a big extruder or something of that nature. The series field is wound right on top of the shunt field. So you can't really see it in this picture. Does that got series fields in it? That field frame? Let's take a walk. Let's go down over here. Oh yeah, it's got big series fields in it. This is a DC field frame. In here you've got your shunt fields, okay? Ooh, that's a magnet. And then wound right over the top of it. See these conductors here? These smaller wires are coming off the shunt field. These are coming off the series field. It's wound right on top of that shunt field. And then here's your interpoles. Here. Now the reason that's important is because when we start talking about polarity of these fields, the polarity of that series field is important, that it's the same relationship as the shunt field. Otherwise that series field will cancel out the shunt field strength. So what determines strength of a field is the number of turns, and the shunt field has a lot of turns of smaller wire, and the amount of current that's flowing through it. So if you've got, say, 200 turns at 2 amps, that'd be 400 amp turns here in your shunt field. You might only have one turn, a series field, with 400 amps. You still got 400 amp turns. So you could conceivably cancel out your shunt field completely if it's hooked in the opposite polarity of the shunt field. All right, let's go sit down. Unless anybody's got questions about this thing. If you got questions, just ask, because it's...
What's that power?
What's that power? That power is a Banbury mixer.
Yes.
Makes rubber. Belongs to BRC rubber. The armature is in that lathe right over there. Trying to think if we should... Yeah, let's walk over here too. What the hell, we're gonna make this a walking tour. Walk down here by the commutator end. Each one of these is a copper segment that is insulated from each other with a strip of insulator that's generally made out of mica, which is an excellent insulator, and it's made from a rock. Each one of these then are in turn connected to an individual coil that will span around, say if there's a 1 to 12 pitch, that coil may span 12 segments. The opposite end of the coil will come out on the opposite side, which is directly opposite of this one. So if this end is connected to this end of the coil, then the other one is actually one past halfway on the comm. Now the brushes are going to ride right on top of this, generally covering at least 2 or 3 segments. So as this is rotating, it's commutating voltage to the appropriate coil as it's positioned in this armature. I wish I had a commutator that was all tore apart, but I don't think I do. You don't want us to wind this and...
Sorry.
No? Okay.
Unless it's training.
You know that ain't gonna happen.
I know that.
All right, so that's much better in this picture. All right, now in here, in this handout I gave you, I think we need to look at two pages at once because I didn't get them both on the same page here. The page that's titled armature is referring to the picture on the next page. A two-coil illustration. What we're seeing there and we're going back to our induction theory back here, is we're seeing that this coil here that's perpendicular to the pole pieces, as it's sitting there in a moment of time, it's right in the middle of that field, right? So if you hold that magnet in the middle of that coil, there's no voltage or current induced into it at all. That is the primary moment for us to apply voltage to that coil from our drive. So when we power up this armature, we're going to have this commutator segment connected to the coil that is in perpendicular position to the pole pieces. Now in the meantime, we got all these other coils in there that are doing what? They're spinning inside of this field, right? And what's happening? We're inducing voltage into those coils. So as those coils that aren't connected to the brushes are rotating within that field, we're inducing a voltage, an actual AC voltage into those coils. So with the exception of the one coil that's perpendicular to the pole pieces, we have AC current flowing in all the other coils. Now, that's what's called back EMF, and that's what limits the current within the armature itself, and also will allow you to, who's putting ohm meter on an armature on A1 and A2 to measure the resistance of that circuit? What do you got? You got almost nothing, right? If you got a couple ohms there, you're lucky. I mean, maybe on a small one you got a couple ohms. Ohm's law says that the voltage is equal to the current times the resistance, right? So how the hell can you put 500 volts on a 2 ohm load without pulling 250 amps? Well, if it wasn't for back EMF or that AC generated voltage that's within all the rest of the armature, you couldn't. So what's going to control the back EMF is generally two things. The speed. If you notice, the faster we move that magnet in and out of that coil, the higher the needle pegs, right? So the faster it rotates, the more back EMF we have, and the stronger that these fields are, the more back EMF we're going to have. So that's what's limiting your armature current. All right? So if you're in a situation and you've got a motor out there and it's pulling high current on the armature, you're getting an overcurrent fault on your drive, and you're going over and you're checking it out. Well, the load's good. Looks like it should be all right. I mean, we're getting good output from the drive, but we're still getting overcurrent fault. The thing to do is what controls this strength of these fields is that coil that's wound around that pole piece. Do you got enough current there? If you got enough current, maybe you've got shorts in that winding that's affecting the field strength. Amps times turns determine the strength of that field. So if the coil started out with, say, 200 turns and you've overheated it, or the enamel on that wire started to break down and you've got some shorts, now maybe you've only got 150 or 100 effective turns left in that winding. That cuts that field strength in half if it goes to 100, which cuts your back EMF in half, and that makes what happened to the armature current. It goes up. So that's a good place to look if you have a situation where you're getting overcurrent faults on a drive or you're getting high armature current. Once you've established that, then you could move on to something else. If generally that information is on the nameplate, if it's not directly on the nameplate, then you may have to do a little bit of math to figure it out. But that's just arithmetic, actually. I wouldn't even call that math. So now, when you're measuring resistance of a shunt field, keep in mind that those fields, they will go up in resistance from a cold field to a warm field by about 25%, 20 to 25%. So on the nameplate, if you see it, it'll say, 75 ohms at 25 degrees C. You know, that's, and you measure it and it's like 90. Well, it's because it's hot, because the resistance will go up quite a bit. But what it won't do is it won't go down. So what you're looking for is something that should be 90 or 100 ohms, and it's 35 or 40. And that's a failed shunt field. If you guys have questions, blurt them out. Still kind of talking about motor components for some reason. Kind of hit this already. Brush rigging commutates the current to the armature coil that is under the brush, and it also sets up the timing between the armature coils and the shunt field. Now, I mentioned that we use that for setting brush neutral, and the way that we do that is we hook those two small leads that I was using for that microamp meter to two adjacent brush holders. So we'd hook it to these two. And then we take, on the shunt field, there's a power supply, there's a DC power supply built into that little homemade thing. And we'll just do this. We'll just hit the wire and come off of it. We'll get some current flowing, maybe a couple amps or something, and then we'll just do that. And we'll watch that amp meter, and what'll happen is if this coil isn't exactly perpendicular to this holder, then that needle will move. And you can rotate the brush holder off of, say, the segment of the comm that it was on onto an adjacent one, and you'll see the needle move. And then you keep doing that until that needle doesn't move. Now at that point in time, you know that brush rigging is set properly because there's no induced voltage into it because it's perfectly perpendicular with the field. We're making AC by flashing it with the DC, on, off, on, off, on, off, and then just observing the position of that coil by virtue of that little microamp meter. You guys all seen a brush rigging? You know what it looks like. Holds the brushes, got springs in it, holds all that. It's always got slots in it that you can rotate that rigging around. What we see happen frequently is that somebody decides they're going to change the brushes in the motor, and like a 4-pole have like 4 brushes, but this one here on the bottom is kind of hard to get to, and they'll go, oh well, hell, it's got bolts on it, it's got slots, we'll just rotate that up so I can reach it. You know, you're down there on your, you know, belly trying to change brushes, so it's easier if you just spin that thing around, you know, and well, then they'll tighten the brush rigging back up, turn it on, and all of a sudden there's a ring of fire around the comm. And the reason for that is that your back EMF, that voltage that you're generating and all that in the coils that are right over the top of the brushes, is meeting the voltage going in. So you got them meeting at the same junction, and it creates a spark. Sometimes a pretty good ring of fire too. Depends how far off it is and how high that potential is in that back EMF. So if you have to move a brush holder, plan on being real careful about marking the position of it. You can take a scribe knife or something like that. Now generally what these guys do is they pull a hole and end bell off, and they set it on the table, and then they'll take their drill with about an 1/8 inch drill bit in it, and they'll mark it, 2 spots, one on the stationary housing, one on the phenolic ring that the holders are connected to. So if the motor's ever been in here before, you might be able to locate those drill marks. If you go, oh shit, I loosened that thing up and I shouldn't have done that, kind of thing, that oh shit moment. Otherwise, it really just needs to be reset. And I mean, we just made that thing. We can drag it out in the field and do it there too. So, the point of caution. A lot of people think once their brushes start sparking, that means you got to replace the brushes. Well, that almost never really works. It's just if they're too short or the spring tension's loose. If they're that short, normally the clips are starting to grind into the comm, and it's too late by then anyway. So the thing has to come out. The brushes riding on that mica, boom, it's going to turn to carbon dust in no time. And then that carbon is pretty conductive, so it's going to just kind of fill up into the armature and then create grounding points and just all kinds of grief. So if you get grooved comms that are down to where the brushes are riding like actually off that, you saw the undercut between the comm segments over there. If it's riding on that mica, those brushes aren't going to last. It's just going to cause you more problems. It's easier to get it out, turn the comm. We've got a machine to undercut those mica slots, get it all cleaned up for you. This is an illustration of a phenomenon called armature reaction, and we'll explain the reason for interpoles. You guys all got power tools that run off of AC or DC or whatever. They got that little universal motor in them. You've all taken them apart probably, and you just see two poles and a couple brushes, and they go like a bat out of hell. They're little Series 1 motors, but they almost always spark. They almost always are sparking at the comm. The reason for that is because when that armature's spinning in that field, it bends it, okay? And it bends that field to the point to where, I don't really have anything other than that, but it bends that to the point to where it actually starts to come all the way across and interfere with this flux field of this one. Now we're getting back to kind of the same thing with the back EMF or the AC current getting generated into coils it's not supposed to get generated into, and they're right under the brush, and then they, sparks at the comm. So the answer to that is you put an interpole in here, and it's positioned right between each of the stationary poles, and it's connected in the same polarity as the main pole. Going the wrong way. It's connected in the same polarity as the main pole preceding it in direction of rotation. So if you're turning this way, and this is a north pole, then this is going to be a north pole. If this is a south, this is going to be a south. Now, naturally, these have to be opposite polarity. These are the same, and these are the same. So you got north, south, north, south. That's how they're connected internally. Same thing with the interpoles. If that's a north, you got to make this a north. This one's got to be a south. Now the reason for that is because like poles attract. So as this flux field starts to get bent from that armature rotating inside of that field, the invisible field begins to move. And what you don't want is you don't want it to get over here and interfere with this south pole. You want to keep that north pole flux confined. So what that interpole does is it attracts that flux and keeps that flux field right where you want it. It just, the only function of that interpole is to keep that flux field confined, in this particular case, 4 quadrants. If you've got 2, there's 2. If you've got 6, there's 6. So same number of interpoles as stationary fields, because they're there just to keep that stationary field in the area that you need it. Because if it's not, then it will create sparking at the com wear, premature brush failure, and that could be a reason for sparking at the com too, is if you have an interpole that's bad or one that's grounded or something like that. We talked about the series field canceling out the shunt field. And if that happens, that's really no different than having a shorted field or having one with low or no voltage on it, or low or no current on it. And because that's wound on top of that, the polarity of that thing needs to be the same. And if you, there's some DC motor connections in this book. The straight shunt motor is really, most of the motors that you see now are just straight shunt motors. You can buy a compound wound motor. Sometimes on the nameplate it'll say stabilized shunt. That's what they call it. The series field, if you've got one, is called a compound motor or a stabilized shunt motor, and the connection for that is shown here. This is normal NEMA wiring scheme. So you got A2 goes to S1. That keeps the series field the same polarity as the shunt field. When the shunt field is F1 is positive. Sometimes we get them in here and they're not marked. Whenever they go out, they are. So we'll put this standard marking on the motor leads before it goes back. If you put colors or other markings on there to help you put it in, we'll put those, we'll leave those on, or put them, you know, keep it that way so you can match them up. But we'll also add those numbers to it. If you put it in and it runs backwards and it's a compounded motor, you need to, and you want to change the direction of rotation, you have to change A1 and A2. Or you can walk up to the drive maybe and just change it that way. But if you change, this can be kind of a pain in the ass because it's, you know, bigger wire, especially when you get into some bigger motors. You got to break that S1, S2 connection open, and it's all taped up. And then you got to break the A1, you got to change those around. So it could be real tempting just to change the whole circuit by going to your drive and pulling out A1 and A2 and switching those. But if you do that, you're changing the polarity of that series field at the same time in relationship to the shunt field, which is going to differentially compound that the motor stationary field. And when you pass current through it, the higher the current, the more it's going to cancel it out. It's connected in series with the armature. You may run it no load, looks fine. Put a load on it, the higher the load, the less back EMF you got, because it's canceling out your back EMF, and the current just goes up. And you know, I don't get it. A couple of load runs fine. So that's important. The only way to counteract that is to do it properly by changing A1 and A2 and make sure that you keep the series field the same polarity as the shunt field. or walk up to the drive keypad and change change it that way, which is usually pretty easy to do. Series wound DC motors, I can talk about that for a minute. I mean, essentially a series wound motor, you get a lot of torque in a small package. You can't regulate the speed on them at all. The speed is totally load dependent. The more load you put on it, the slower it goes. Like your drill motor or saw or something like that, I mean, you can noticeably notice the speed of it coming down. Another example of that is like a golf cart. Those have series wound motors because you got a, you know, small package, a lot of torque. Actually, the best use of a series motor as far as industrial use is on a locomotive. Locomotives have trains that go by. The locomotive has series wound electric motors on it. That diesel engine you hear revving up is a generator, and all it does is make power, send it to those motors that are coupled directly to the axle. So they control the speed, well, not real well, as you can see. You can't speed a train or slow it down real quick, but they get a lot of torque. And there's about, most of them have 6 or 8 motors that are probably about the size of this table to about here, and about the same height. And they're right on, they bolt right to the axle. And you see what they do, man. They drag all kinds of weight down the tracks. If they tried to do that with a compound motor, they just couldn't. You couldn't do it. It'd just be too much, too big. Starter in your car is a series motor. So if you ever have a solenoid brake, and you just keep hitting it and you hear that starter motor just whine up like it's gonna, it will, if you stay right on it, it'll fly apart, because it'll just keep picking up speed with no load on it. It'll just keep picking up speed, and then centrifugal force will just fly that thing apart. I mean, comm segments will come flying out, busting up the brush rigging and all kinds of stuff. I actually saw it happen on a big mill motor over at Inco Alloys in Elkhart. I think they're gone now, but they had a mill, nickel mill, and he called me. This is a motor that's probably twice the size of that DC motor down there. And he called me up, it was like 3 in the morning, and I don't know, I thought he's having a heart attack or something. He was just completely freaked out, and he's like, "Get over here as soon as you can." I said, "All right." So I got over there in about a half an hour, and literally the room is probably about, well, maybe about half the size of this one where the motors are, and the shafts go through the wall, and then the mill's on the opposite side of the wall. So they got an overhead door, and I just walked right in the overhead door, and it was raining mica. Because this motor just physically, we got pictures around here someplace of it. I should dig those out because it's pretty impressive. But the comm segments come apart in it. It wiped out everything. And the mica that's in between the comm segments got airborne, and it was just flaked. It looked like it was snowing in there. It was just insulation and copper and everywhere, because they lost control of it. Apparently that was because they lost feedback and their drive didn't fault out or trip or anything. The mill just took off. It broke out. What had happened is, in a mill like that, if the load breaks out, then you've got that motor, it's under a lot of power. I mean, about 1600 amps. And if they got that thing running at, say, 400 or 500 foot a minute, that motor's cooking along. It's probably going 1,200 RPM. And you got an armature that's probably that big in diameter, so it's a lot of inertia. Everything is, physics is just taking over. And then it breaks out, and there's an overspeed switch on the back side of it in addition to tach feedback. Well, for some reason the drive didn't fault on tach feedback. The overspeed switch failed. Who knows when, because that's something else we were talking about, preventive maintenance. They just assumed it was working, probably never checked it, you know. But it had failed, and so the drive just kept pouring the coals. Just kept pouring the coals to it, man. Without a load, the current probably wasn't that high until it started flying apart, you know. I'll see if I can find those pictures. They're pretty impressive. AC. We're gonna move to AC. You guys got questions on DC? We are DC motor experts. In 45 minutes. Okay, these phases are put in, this is like there's groups. The number of groups is determined by the number of poles. So a 4-pole motor has 4 groups in each phase, right? So times 3 phases, so there's 12 groups total. So the number of coils in each group is determined by the number of slots. So we do some arithmetic and we determine, okay, well, we need, like that one there looks like it's got, what, 6 coils per group? It's probably a 4-pole. Each one of these, this phase paper that goes in between here, that's separating A phase from B phase. This one is physically put in the opposite direction. If they make a full group, they might put one on straight. It's still connected to the next group. Physically rotate it, put it on, put the next one on straight, turn this one, so that essentially what we're doing is, by doing that in A phase, we're changing the polarity of each pole, because it changes the direction of rotation or the direction of current flow within the coil. So if this is A phase, then it's going to be, say, at any half cycle, a north pole. At the same time, this is going to be B phase, and it's going to be a south pole. And if we go all the way back to our sine wave, as A phase reaches peak positive and starts to fall to 0, B phase is at peak, and as it's fallen to 0, C phase is at its peak, and then they go opposite polarity. So this will go north, south, and if you're running it off as straight across the line, at 60 times a second that happens. So what it does is it creates actually a rotating magnetic field that is just chasing itself in a circle. That's what the winding looks like after it's all connected and tied down, before it's varnished. Once it's to this point, it's tested, and then it's varnished to keep everything. It's moisture resistance and rigidity. Keeps everything from vibrating in there and creating problems. But in the big scheme of things, this is a 4-pole. So we'd have, if we have a north pole here, south, north, that's 1 pole. North, south, north, that's the 2nd pole. North, south, north, 3rd, same thing. So that current is just chasing itself in a circle. And it'll do that whether you got a rotor in it or not. Pull a lot more current without a rotor in it, but it will do it. Different connections here. These are also in this book. This is a Wye connection. Generally, this is on your smaller, say below 50 horsepower. The reason for that is because if this is one phase, say A phase, B phase, C phase, when you put 460 volts from this terminal to this terminal, you're actually only got about half. It's the vectorial sum of 3, the square root of 3 times applied, but suffice to say it's 277 volts to the neutral in a Wye connection. So you don't have as much voltage and the same number of coil turns on a Wye connected motor as you do a delta connected motor. Because in a delta connected motor, your phase voltage goes across just 2 or one whole phase. See the difference? Now the reason that this works out okay, better on smaller motors is because normally smaller motors by design require more turns per coil, and the wire size is generally bigger. So you want to go, if you got to only cover 277 volts, then you don't have to have quite as many turns as you do when you got to have 480. So it works out nice because in a delta, they go to the delta connection. Theory is exactly the same. So you still got the rotating magnetic field. It's all about putting the right number of amp turns on each one of these phases. You get to a bigger one, and you know, if that motor was connected Y and it only had 8 turns to begin with, you're down to like 4 or 5 turns now. And your wire size is a lot bigger than you want it to be. So it's a lot more difficult to wind. It's more copper losses and things of that nature. So this shows the low voltage connection, which is essentially a parallel connection, while this is a series connection. You'll see a lot of particularly foreign motors, they'll bring all 12 leads out. So what they're doing is like this one, they'll bring their neutral point out externally. Some motors are set up for a transition starter, like you might have a 12 lead motor that's, or even 6 leads that's marked Y start delta run. They want to soft start it. So they'll start, mind you, we've got a winding that's rated to run at a phase voltage of 480 volts, but we're going to start it on a Y and only put 277 volts on it. That's going to give it a soft start. Once it's up to speed, we're going to switch it over to delta, and we're going to give it its full voltage so we get full torque. A lot of import motors I have 12 leads on because they do tri-volt stuff, you know, like 380 volt, or they find compromises with the voltage. You'll see some of them are low voltage is a Y and a high voltage is delta. Well, it's not a perfect world. They just find some happy medium, because low voltage is not the same as 277 volts, because you're going to put 230 on it. It's not going to really quite have 277 on it, so they'll find somewhere in the middle and design the winding for like 250, put 277 on it, it'll be all right. 480, they're going to be overvolting it a little bit, yeah, it'll be all right, that kind of thing. Talk about the rotor. This is a squirrel cage, cutaway of a squirrel cage motor. You see the rotor here on the outside is cast aluminum. These are laminates. When I say laminates, I mean they're individual iron pieces that are stacked on top of one another and insulated from one another. You can see it if you inspect these stators or any of the stuff that's sitting around here, the rotors, all that. If you look close, you'll see that they're insulated. Now the reason that they are is because induced voltages into a ferrous material like carbon steel is going to induce voltages. So you're going to have current, flowing in your iron, which is just going to make heat. Okay, so they laminate it, insulate the laminates from one another to reduce that eddy currents, they call them. Now what the rotor really looks like when we strip it away is that. Generally a squirrel cage rotor is poured aluminum, like it's a cast aluminum, but it's a winding in and itself and an integral part of the motor, because a voltage is getting induced into that winding in the relative polarity that is correct for its position in the rotor. And that's all happening because of that rotating magnetic field. And it causes these magnets to chase that current in a circle. And the stronger it is, the more torque it makes. So it's just as much a part of the winding as everything else. Now once you get it up to full speed, then the voltages drop off pretty significantly once you get closer to base speed or synchronous speed. Like on a 4-pole, that's 1800 RPM. That's determined by the number of poles and the operating frequency. So the formula for that is 120, which is a constant, times the operating frequency divided by the number of poles. This is fixed. This is fixed. This we can change with a drive. But if you just run across the line, it's 60 hertz. If you do the arithmetic, it's 120 times 60 divided by 4. It's going to come out to 1800 every time. Now it may say 1800, but it's never going to run 1800. It's going to run something less than that. 1765, 1750, 1725. The difference is slip. It's what's called slip. The more slip you have, the more rotor current you have. Some applications require a lot of rotor current, like a high, it's like a stamping press. It's got to start a big giant flywheel, or it's going to slow down naturally because it's going to see that big load every time that press hits. It's going to really grind down on that motor, so the motor's going to just try to slow down, and then it'll speed back up when the load comes off, and it's going to do that all day long. You can't really use aluminum cage, squirrel cage rotors for that. It'll melt them, because aluminum has a pretty low melting point. Generally those are a copper alloy, a lot more tolerant of heat in a design D, high slip motor. So if you've got an application like that and you look at the nameplate and it says 1685 RPM or something like that, I mean, you could have like a 3 or design B or a squirrel cage type design is up to like maybe a 3% slip. You get into a design D, you could have as much as 13% slip. You could have a 10% slip, 8. Don't replace those with just a standard off-the-shelf squirrel cage motor, because it'll melt the rotor right out of them. I've seen that happen. Don't think 1800 is better than 1650 if your nameplate. So it's real important to know. There's your Flux Fields 6-pole. The only reason I'm illustrating this is because I'm trying to illustrate that two things. One, the reason that it doesn't have to go. All right, I'm going to put this differently. Your rotor's spinning in here, and for every half cycle, it's going to move from one pole to the next, right? In a 4-pole motor, it has to move from here to here, 1/4 of the way around. In an 8-pole motor, it only has to go it's only going to go that far. So that's why an 8-pole motor will go half as fast as a 4-pole motor, because in the same period of time, it's going to go half the distance. 6-pole, 1/3, etc. Now what that does is, by adding poles, you add torque capability. So a lower base speed motor will have more torque than a higher one. So a 5 horse at 1800 RPM will not make the same amount of torque as a 5 horse at 12. A 5 horse at 12 will make 33% more torque than a 5 horse at 18. If you want to replace a 5 horse at 18 and you want to go to a 1200 RPM motor and you want to go to 18, you're going to have to go 33% higher in horsepower to do that. And that's also why you'll see, if you look at a motor frame chart, you'll see that as the poles go up or the base RPM goes down, the motor frame gets larger. Torque is horsepower times 5250 divided by RPM. So as you can see, the denominator in that formula is RPM. So when you're dividing into RPM, your torque is higher. Difference between constant and variable torque. Constant torque applications, they require the same torque at all speeds, so horsepower is variable. Constant torque, mixers, extruders, probably the biggest lion's share of manufacturing type applications. Pumps, fans, all variable torque loads. If you drop the speed of a variable torque load, the current just goes right in the bucket, man. You can save a lot of money if you lower the speed. A lot of plants will have a air makeup unit or a pump, and you're changing the volume or the work it's doing by throttling a valve. Throttle a water valve, throttle inlet valve on a air makeup unit. You're not utilizing all you got. I mean, if you just took and replaced that with like a 4 to 20 milliamp transducer, feed that into a speed control unit, a variable speed drive, and let that transducer do the work instead of that valve, it would keep everything at the right pressure, right, whether that's static pressure or whether it's line pressure or water pressure, and the current on that thing would be significantly less, like 3 times less. A 10% reduction in RPM can make a 30% difference in current draw. Current draw on your meter is kilowatts. That's what AEP charges you for.